Welcome back, Dr. Elnasser, in part 4, in which we will delve more in the incapability principle. So please go ahead and you can, I have already opened the share, yeah, and you can share your precious slides.
Okay, so last time we stopped here where I was briefly discussing the boundaries of formal systems, especially those made for math, physics, and also in general, formal systems in general, in particular math and physics. Now, and we spoke about the incapability principles. We mentioned them many times, but now we are going to delve a little deeper in these incapability principles in modern epistemology, especially from the point of view, first from the point, we'll talk a little about modern philosophy of science. You see here on the left, the three main or known philosophies of science. You see here Karl Popper. For Karl Popper, each theory builds progressively on the theories preceding it. So I have a certain theory, and then I expand it to become theory number 2, and then it becomes theory number 3. So actually there is an expansion of science going on. From the structural point of view, science is expanding for Karl Popper. It's not falsifying its own theorems. It's just expanding. For Kuhn, it's not like this. Kuhn says that the paradigms are incommensurate and encompass some parts of previous paradigms but reject other parts. So he's saying that there might be some common theories or some common
points of intersection.
Some point of intersection between the theories, but they are not including each other. This means that previous paradigms may be rejected completely. And the third one, Feyerabend, theories have little to do with previous theories and are not coherent or consistent. So Feyerabend is actually more the
He's more radical.
Yeah, the guy who
prefers,
as
his famous book Against Method.
Yeah, exactly. So he's known to prefer chaos theories to other constructive ways. I myself, I'm more inclined towards Popper, although of course some of it's not really, the circles are not really included in each other like they are shown here, and it's only a simplification what's shown here. Actually, there are, of course, some theories which are rejected, but most of the theories, and here we are speaking about, especially about physics in this case, of course, Popper, Kuhn, and Feyerabend were speaking about natural sciences. They are not, they were not generalizing in the context of mathematical sciences or theoretical sciences. So let's go back to the physical law. As we said before, a physical law is to form a new physical law, you have 3 steps. An informed guess. So I have a certain bulk of information, of experimental information, and then I think about them. I use induction, incomplete induction, to form a certain guess of what the law might be. And this guess should be general enough to have consequences. So this means it includes many things. It explains also many things. And it should also be experimentally falsifiable, as we saw. Now, this means that a successful experiment is not a verification of a law. When I do an experiment, I don't verify the law, but it might result in its falsification. So I do an experiment, and in my mind is not a verification to the law which I guessed, but an attempt to falsify what I hypothesized. So this means that if I do many experiments showing that a certain S is true, then I will get, as we discussed in the previous lecture or part of the lecture, I will get objective scientific evidence leading to empirical belief for S. So I have an empirical belief that S is true. If I do many experiments showing S, the experiment shows S, or to be more frank, it doesn't falsify S, then there is I have a belief that S is indeed, might indeed be true. Now, what is an informed guess? If we think about it, the informed guess is, first of all, you will have to have a history of experimental data trials. Yeah. So, for example, you cannot do 2, 3 experiments and then say it's an informed guess. Yeah. But usually you do, especially in physics, you do thousands of experiments, and from the history of your experimental data, you can generalize either positive or negative rules. Means either it's probably correct what I asserted, or it's probably not possible. Now, all generalizations related to this S, which I experimented about, lead to the objective scientific evidence and the belief. The negative generalizations, which actually are falsifications. So I want to show S, but whenever I do an experiment, I get not S. I get the opposite of S. Yeah. So I'm trying to do S.
It refutes my hypothesis.
But I'm trying to do S, but I can't. So when I do like 1,000 trials of getting S, but I fail, here comes the incapability. So the incapability. So after 1,000 trials of trying to do S but failing, I will say, okay, then there is a law. There might be a law. I can make a hypothesis that S is not achievable, actually. Yeah, which makes a lot of sense. And it is, of course, incomplete induction. Now, incapability principles in physics have a very, very famous examples. Like, for example, one of the first usages of this incapability was the perpetuum mobile idea. People wanted to make, in the beginning of last century, and since the middle of the 19th century, they were always trying to make a machine which works without fuel. Yeah, a machine which will continue working alone without needing fuel. So for for decades they tried to do this, and it's called the Latin expression is perpetuum mobile. So this perpetuum mobile idea failed, and it led to energy conservation laws. It led to one of the most important laws in physics, which are the energy conservation laws, which show you that you can never. So actually, we are incapable of doing this perpetuum mobile because there are these energy conservation laws. If I put some energy in place, it must come somewhere else. If I don't put, nothing will come. Yeah, so this is the basic understanding. So the energy conservation laws came out of this failure of doing perpetuum mobile. Our incapability of doing perpetuum mobile made us invent the energy conservation laws. Now, another very famous example, failure to find ether. People thought before Einstein that space is filled with a substance called ether. And they tried a lot and experimented a lot to try to prove the existence of ether, but they failed. And this led to a very important observation that light is independent of the observer. So light is actually independent of the observer because of the failure to find ether. We reached the conclusion that light is, or we assumed, we used our incapability to find ether to assume that light is independent of the observer.
Yeah, and this is
And this led, actually, when we say we, it's not me and you, of course. It was Einstein. It was the theoretical, especially Einstein. Einstein hypothesized that light is independent of the observer, and then he came to the
and I think
time-space.
Al-Hassan ibn al-Haytham, I think he corrected the Greek theory.
No, but we are here not. No, we are here somewhere completely
This has to do with
different.
optics.
This is
It has to do with
no,
optics.
yeah, no. This here has to do with the speed of light and all this type of things, and with the constituents of the space of the whether space is void of any substance or containing some substance. So when they failed to, and they assumed that in the beginning of last century, and here I'm always speaking of Western science, of course, it is difficult to make this link to ancient sciences unless it's known, unless we know it. Yeah. So concentrating
Because
only
Al-Hassan,
on
he tried to measure the speed of light.
yeah, I don't know whether this is right or not. I don't have information about it. But it's not important. It's not important. I mean, in this context, it's not important. Because here I'm trying to say that when they failed, when they were incapable of proving the existence of ether, Einstein came with the idea, I think it was Einstein, that light is independent of the observer. And then he came with the time-space concept, of course, and then special relativity. So here, the incapability of finding ether led at the end to special relativity. Failure to distinguish between gravitational and inertial mass brought him then to the general relativity. And this is definitely Einstein. Now, Einstein, they tried a lot, not only Einstein, everybody else at that period tried to distinguish between gravitation and inertia.
We can say that the incapability principle, how to say it, forced somehow the scholars or the scientists to another theories.
Yes, of course, because the incapability principle was like a wall, like they tried to experiment in the direction of a wall, actually. When they found out that there is a wall here, it's useless to continue experimentation because we did already thousands of experiments in this direction. They said, let us assume, and it's now this is an assumption. Again, it's not knowledge, it's belief. So they believed that it is not possible to break this wall. So they believe that it is not possible to find ether, for example. So when they assumed that there is no ether, they came to the idea that light must be independent of observers, and then the time-space concept and special relativity. When they failed to distinguish between gravitation and inertial mass, they came actually here, Einstein, to general relativity. So all in all, incapability in physics is used as a heuristic principle without proof, leading to objective scientific evidence generating empirical belief. So it is an empirical belief that special relativity is actually an empirical belief. General relativity is an empirical belief. It's not knowledge. This is very important. This idea
it's not a fact.
This idea that the big laws of physics are actually not knowledge but belief, assumptions, theorems. This is a very important idea because it breaks completely with the tradition of linking science to absolute truth and to reality. So it has nothing to do with reality. It's actually only a hypothesis made because of the incapability of doing some things. We were incapable constructing perpetuum mobile. Therefore, we got our energy conservation laws. Yeah. So it's very important to remind ourselves always that the principles themselves of physics are, although they are objective scientific evidence, but they lead only to empirical belief and not knowledge. Now, let's go to math. In math, traditionally, a mathematical law for a long time, there was only either proof or no proof. We discussed this. So there is either law or no law. So always there was objective scientific evidence leading to mathematical knowledge, because we had the proof. If you have a proof, then you have mathematical knowledge, and this proof is scientific evidence. You can say, I have scientific evidence in math that this and that because I have a proof. So for a long time, they only accepted proofs, as we discussed before, and scientific evidence was related to this proof, and you will speak about mathematical knowledge, not belief. Now, this changed drastically with Cantor and Gödel. Of course, Cantor is the father of infinite sets, of the mathematics of infinite sets, and then Gödel, we spoke about him. And they, both of them, showed incapability also in math. I didn't mention here Skolem. Skolem is also a guy which should be mentioned with these two. Both of them, I mean, Cantor, as you see here, he died 1918. Gödel remained until late 70s. Yeah. So what they did is they proved with very famous proofs, which for us in computer science are basics. Yeah. And they are basics also because they have directly to do with programming, our incapability to write programs which will never hang, for example. Yeah, is one of the things which all of us know from the first semester. So actually, if you ask theoretical computer scientists, they will tell you most of our science is built upon incapability. So you learn like tons of theorems about what we cannot do algorithmically. We have only, maybe if you ask me, I mean, practically, we can do only 10 types of algorithms. We can actually solve only 10 types of questions, really solve it in a practical way. And the rest is undecidable and unsolvable and very inefficient and all this. So proofs in math are, of course, complete induction, refutation, something called diagonalization. I'm not going through it, of course. And then also another thing called counting argument and incapability in math. Now, the difference between incapability in math, incapability principles in math, and the ones in physics, these are not assumptions anymore. So, for example, some infinite sets cannot be counted. This is knowledge. We have a proof for this. So we have a proof that we have for our incapability a proof. The interesting, the difference between physics and mathematics in the theme of or related to incapability is, while in physics our incapability is only assumed. I am assuming that the uncertainty principle is true. I'm only assuming. In math and in mathematical logics, I know that the incapability is there. So I know that some infinite sets cannot be counted. Yeah, it's knowledge. I know, for example, that deduction is not complete if the language used is powerful enough. This is Gödel's theory. So if I choose a language which is powerful, which is more powerful than the normal arithmetic we are taught in school, then already I know that my deduction is not complete. That means that there are some theorems about numbers which I cannot prove. And there is a proof for that. So his thesis was actually proving, it's a famous thesis. There are thousands of problems which are undecidable and which are proven to be undecidable. Not only undecidable like a hypothesis, no, this time our incapability is provable. And it makes a big difference between physics and math. There are also thousands of decidable ones which are still open for other important angles, like the famous theory of MP completeness. I will not go in its detail. It has to do directly with my work. There is a famous P is not equal to MP conjecture, which can only be belief. Yeah, no one has. I mean, until now, okay, I've worked on this conjecture, so I'm biased actually towards a certain solution to this problem. But the status quo now, what is there now in the state
Academia.
of the art,
Okay, on the
in academia, that this famous P is not equal to P, and P conjecture is only a belief. Yeah, it's not. So for some incapabilities, I am having a proof. For other incapabilities, I just have to believe. I don't have proofs. Of course, I don't have proofs for all my incapabilities. Some of them, but in math, you can have proof for your incapability. While in physics, because it is more experimental, you will not reach a proof because obviously you cannot do infinite number of experiments. So there are many more examples. Now, what are the cognitive problems related to this, our incapability? Of course, if you say until I mean, not now, but until the middle of last century, the people thought that science, it's only a matter of time until science can explain everything and can understand everything, and there is no ceiling for science. But in reality, undecidability of a problem, which especially if this undecidability, like in math, is proven, it's a law. So there is now a law that we have thousands of problems which are undecidable. Now, if math uses only knowledge and only proofs, what shall we do with such a problem? Suppose I find that a problem P is undecidable. Like, for example, a very practical problem. I mean, people might think that those problems are just for theoretical, academic purposes, but there are very serious problems in the praxis, for example, of computer science, which are undecidable problems. Like, for example, writing a program which knows that any other program will fulfill its requirement or not. For example, if you are a programmer, you are employed by some company, it would have been very nice if you can, when you submit your program, submit also a guarantee that your program is doing what it's supposed to do. This problem is undecidable. Many people don't know that this problem is, so it is undecidable that a programmer, the programmer, after he writes, even if he puts all his effort behind the program, there is no guarantee that his program will do the requirement which it should do. So this has a very big effect on the whole industry. It's not. So this is also why the computing devices crash, why they hang. It's called actually the halting problem. So if I have something like the halting problem, and it's a law because I have a proof that my methods make this type of problem unsolvable. I cannot decide whether any program which I write is really doing what it should be, what it should do. It's an amazing, simple
give
thing.
Example from, for example, ChatGPT or this application, this software that you maybe you can give him or the automatic translation of Google. Sometimes it cannot translate some difficult words or technical words or
Well,
poetry.
it's any program, If you have a program, before you write it, you usually have a set of requirements for a program.
Mm,
So what I'm saying that what is undecidable is that when I give you a set of requirements, you are a programmer, and
mm,
you put all your effort in
mm,
programming.
And
You
it's a
still
relative,
you,
relative.
yeah, and you still, with all your knowledge and everything, you still cannot guarantee me that your program will do what I wanted you to program for me. So this
mm,
is whether you use ChatGPT or use whatever anything else. I mean, ChatGPT and this type of new things, they use statistics and probability and all this. I'm speaking here more of things which need a 100% decision. Like, for example, the programs which control the airplanes.
uh-huh.
You don't control airplanes with ChatGPT.
Mm.
Otherwise, I mean, so from time to time, there are more and more accidents now coming out to be a failure of the instruments. Why? Because there is no guarantee that any program I write is really fulfilling the requirement I wanted it to do. This is a very famous undecidable problem. Now, if math uses only knowledge, what shall we do with this type of problem? So the practical solution is to say that we admit belief. The practical solution is to say if we are not able to decide many problems in math, then math should become a little more like natural science. Yeah, like you do hypothesis and work with hypothesis. And a very famous example is the so-called continuum hypothesis, which is a basic hypothesis about number theory and so on, about infinite sets. Yeah, that between two denumberable and uncountable sets, there is a dimension in between. This is called the continuum hypothesis. No one knows whether it is right or wrong. So the question is, can math be based on belief? This is a question which is until now very vivid, but many people, including Gödel himself, he thought that we should treat math as if it was as if it were natural science. So this is the same for all open problems. Now, undecidability in math is a severe restriction also for physics. Why? Because we saw that physics depends on math as a cognitive tool. We saw that the languages of physics is actually math. So if I say that math has some problems, then physics, of course, has also problems. So undecidability is interesting for all languages of a certain expressive power, as we saw, including math. So this means that physics cannot entirely depend on reality. Now, this means if your tool to express the physical phenomena is already not complete and cannot give you the essence of what you are representing, then this means that in physics you cannot speak about reality. So this is another reason why in physics people don't believe anymore that there is any connection between what they are doing and what is really out there. Yeah. The first reason was that their measurements can never be accurate. There is this uncertainty principle, which is a principle and incapability in physics. But the second is that there is also incapability in math, which makes math actually not reflecting reality as it should be. So these cognitive problems are now very known. Whatever we have talked until now about these matters, this is something which is consensus. It's not like people are arguing about. It is consensus.
It's not a debatable. It's not a debatable theme.
Not a debatable thing, yeah. And it will have effect, of course, on the rest of our lecture. Do we have still time, or
I think we have 7 minutes. Yeah.
how many minutes?
7 minutes. Yeah.
Yeah, well, I don't want to go into the pseudoscience. The next lecture will be about pseudoscience, and because until now we have been speaking about science and the structure, the epistemological structure of science. We have been speaking about incapability principles, about the formal systems, and so on. And now I would like for the rest of the first part to talk about pseudoscience. Maybe not now,
Maybe in part
but
5, yeah, we can take it.
yes,
Yeah, in part
for the
5.
next part, I'm going to speak about Western theories about religion, the so-called atheistic revolution in the West, and the end of positivism caused caused by what happened with the Vienna Circle and what happened in the
Karl Popper and yeah.
Karl Popper and all these people. So this will be the theme for the next time. And but let me go. If you have any questions about what you heard,
I
maybe
see.
in the
I have noted during all these our podcasts or lectures, yeah, or rather lectures, they are lectures, that there is a parallel, how to say, pattern between math and physics.
yes, yes. This is
Yeah,
precisely why
and
I brought them together. Of course.
yeah. So is the
Actually, we just said it.
mm,
Math is the language of physics,
mm,
and mathematical logics is the language of math.
mm,
So whatever you can do with physics is linked to what you can do with math. If
mm,
math does not do have some limits, if math has some limits, then of course also physics has some limits. And if mathematical
so
logics
the
have some
problem of
limits, then
physics,
math has limits. And so at the end, you find in the bottom, you find mathematical logics actually.
yeah,
Of
so
course, of course, you can say why. I mean, mathematical logic, math is used in physics and is much more in industry and so on. It's much more important for from the materialistic point of view. So this is why
and
the
practical, yeah,
development.
for practical. So can we say that physics has two st stumbling blocks: the experimental side, some sort of experiments that are not doable or feasible, and two, the problems in mathematics per se.
Yes, of course. Yeah,
Yeah.
it has actually. There are two incapabilities in physics because physics is on top of them. One incapability is in the measurements themselves, in the experimental part, in the empirical part, in the way you are doing your experiments, of course, and the other is in the mathematics because and the other in mathematics has nothing to do with it has only to do with mathematics itself and especially mathematics under the light of logics, i.e., when I look at mathematics from the logical point of view, I get these incapabilities. Yeah. At the end, they wanted, at the end, if you remember, I mean, all this since Leibniz, they wanted something like a perpetuum mobile for thinking. They
A kind
wanted,
of utopia.
yeah, they wanted a machine which can think and so on. And until now, you can find it, of course, in the cinema and all this utopia of a thinking machine, Terminator. Now,
Scientific fiction, yeah.
when ChatGPT comes now, all of a sudden they are speaking again of all this utopia, which we know it's not it will never happen because even the elementary things, the machines cannot even provide the elementary things. Yeah? You
So
have any other question in mind?
no,
I want
it's
to be sure that at least you got
It was
whatever
a defined
I'm
display
saying.
of it was a defined display for the philosophy of science, and now we know how, at least me, I
So,
have
so if
understood.
I ask you, let me ask you just to know whether you have you got my main points. What are the most important things which you learned until now from this series of parts of the lecture?
Yeah, that science is not absolute, and it's limited, and it has limitations, and the scientists and the scholars don't claim that they know everything, or they have a control over, or they can study all phenomena. So it means that we have a relative knowledge as relative beings.
Yeah, but what would you, for example, say about knowledge and belief? If we, because when we speak about
Uh,
epistemology, we
mm,
always have this idea: do we know really what is happening, or only believe it? What can you say about it? What did you understand from all this until now?
um, I think it's
I mean, there is always an example which I give.
mm,
Would you be if I told you, for example, you bet all your money